I hope I can be coherent. I got off a plane just yesterday that brought me back from Asia, so I've been through 11 time zones in the last 48 hours, and I think I'm maybe firing on 3 of my usual 4 cylinders right now. So bear with me. But yes, I want to talk about climate change with you today, and it is the subject of a forthcoming book. This is the cover, actually, pretty recently arrived on my computer, and the book's going to come out in October with Oxford. And so, if we can have the next slide. So I'm going to be going over what are essentially a lot of the illustrations in the book to talk about this, and this is a graph that consolidates temperature readings from all around the planet. It was assembled by NASA GISS. GISS is Goddard Institute for Space Studies. It's located in New York City, adjunct to Columbia University. And this is where James Hansen, if you've ever heard of him, where James Hansen works. He's probably the best known and most vocal climate scientist in the United States. And this is the work that NASA has done on world temperature. There are other research entities around the globe, one notably at East Anglia University in the UK. That's the operation that was subject to the hacked emails and the dispute over that information. There's another research institute in Tokyo that does this kind of thing. So one of the points I want to make is that even if you think there is some substance to the so-called climate gate over the hacked emails at East Anglia, which I do not think. I think if you look at that, you see scientists behaving more or less as humans and talking about things more or less as humans. Even if you think that episode impugns the data from East Anglia, we've still got the data from NASA, we've still got the data from Tokyo, which say the same thing. And look at this. This is the area of uncertainty for these data. And you can see that the trend goes far beyond the small range of uncertainty within these data. The world is getting a lot hotter. Can we have the next one? And here's what I think should be a fundamental icon of our time, an image that everyone should know and recognize. This is the Keeling curve. And there are 2 interesting stories about this. David Keeling was a recently minted PhD from Caltech in 1958. When he went out with money, I think, from the Scripps Institute, to Mauna Loa in 1958 to install an apparatus that he had helped develop that would measure atmospheric CO2. So Keeling goes to Mauna Loa in Hawaii, on the Big Island, and installs this thing up at the top of the mountain, at the top of the volcano, where the air coming to it is from the trade winds, as thoroughly mixed as any air at that elevation on the planet can be. A perfect sample of the Earth's atmosphere. And he begins measuring atmospheric CO2. 1958. And in just a couple of years, he makes 2 profound discoveries. One is that the amount of CO2 in the Earth's atmosphere varies intra-annually. It's higher. I have to think for a moment, especially in my current condition. This is the summer. Atmospheric CO2 is lowest in the North American summer, highest in the North American winter. Low again, high again. This seasonal variation, what Keeling found, was a kind of annual breathing in and breathing out of the Earth. And the reason for this is very obvious and fairly interesting. Can you shift that just so people can read the data line here? We can push it back in a second. But basically, most of the landmass on Earth is in the northern hemisphere. And therefore, most of the green plants on the Earth are in the northern hemisphere. And so when these plants leaf out in the summer, the uptake of atmospheric CO2 as a result of photosynthesis is greatest, and atmospheric CO2 drops. In the winter, after leaves have fallen, after the grasses have died back, after the photosynthesis is pretty much on hold, except a little bit among conifers and a few other kinds of plants, CO2 rises because the plants aren't taking it up. So that's the disproportionate influence of the northern hemisphere on the atmosphere of the planet. So this is the respiration of Earth taking place through the year. Now the other thing Keeling almost right away discovered was that the mean value of CO2 was going up. And this is what he became most famous for, and this is the beginning of the climate warning, even though we've known about it theoretically since the late 18th, early 19th century, theoretically. But here were measurements that showed that mean CO2 was increasing year by year. Back there in 1958, it was about 315 parts per million. Today, way over here, we're up there nudging 390 parts per million in a very steady, slightly accelerating rise. Well, even at the outset, these first years of data were important enough that the National Academy of Sciences briefed the new President Lyndon Johnson on this matter in late 1963. He said, there's a strong chance our atmosphere is going to warm significantly, and that climate will change over time. We've known about this a long time. So anyhow, here's this curve since Keeling started his work, and Keeling, I think, retired in the 70s. He died in the 90s. It continues as part of the Scripps CO2 program run by his son, who's a very nice man and allowed me to use this graph in my book. Other research drawing on fossil air in ice cores in Antarctica and especially in Greenland have allowed us to sort of retro run this graph. And until the Industrial Revolution, atmospheric CO2 was rising very, very slightly on Earth, but hovering around 280 parts per million, 275, 280 before the Industrial Revolution. So now we're up here at 390 roughly, and incidentally, this increase has been sort of checked against every set of variables we can think of, we being the greater scientific community. Solar radiation cycles, wobbles in the Earth's orbit, you name it. And nothing, I'm sorry, the rise in temperature has been checked against all those things, but nothing has stood up to the correlation except for this. And this is why it is not a matter of conjecture, it is not a matter of debate, but it is a matter of broad scientific consensus throughout the world that the rise in the Earth's temperature that we saw in the previous graph is owed to a rise in anthropomorphic activity, human activity, putting out those greenhouse gases, causing the rise in CO2 and other gases, methane, in the atmosphere since the Industrial Revolution. Let's go to the next one. So, have you ever wondered about the location of deserts in the world? If you look at a map of deserts, you see that most of them are centered at about 30 degrees north latitude and 30 degrees south latitude. Coincidence? As my children would say, I think not. Let's have the next one. So here's one of the reasons that the deserts tend to be centered at 30 degrees north and south. And here's the basic problem of climate change. And that is that the Earth, think of the Earth as a system, and if you pump more energy into the system, more heat energy, that system has to move that heat out and distribute it. Second law of thermodynamics: in a closed system, heat energy has got to spread out, and so the whole system tends toward an equal energy level. The way the Earth does that, most of the energy, or the greater part of the energy, is received near, the greatest amount of energy is received near the equator. That's what gets the greatest heat. That's why I was really cooking in Hanoi a couple of days ago. And so what happens is this heat, which comes into the atmosphere and into the oceans, needs to spread toward the poles. Okay, so the way it spreads toward the poles in the air is the air rises. First of all, from the warmer seas, it picks up a whole lot more water, a whole lot more moisture. Rises. As it rises, it cools. That water comes out. That's why the tropics are so wet, so much rain there. And the hot air rises and it hits the troposphere, the boundary line in the atmosphere that I can't really explain to you. And it starts at that point moving toward the poles, north in the north hemisphere, south in the south hemisphere. So it's coming up here, it's coming up, and then it starts moving toward the poles, and then it begins to descend in a circle, or in a circuit. And when it descends, it heats as it comes down, and this is dry air now, because it lost its moisture as it was rising here in the tropics. And so as it is descending, it's dry. And so this is called the Hadley cell, named after an English scientist who was trying to figure out what made the trade winds blow and came up with a very good answer that's still pretty much the answer, though it's been modified some. So where the Hadley cell descends, you have hot, dry air coming down. And it comes down roughly along 30 degrees north and 30 degrees south. So in a nutshell, that's why many of the deserts, not all of them, but why many of the deserts are located where they are. And that's why the American Southwest is as dry as it is. I can't remember what latitude we are here, 32? 35? So this is down in Mexico. Tucson is, I think, 32 maybe. Socorro would be maybe 34, 33, something like that. Anyhow, the Hadley cell is a fundamental circulation in the planet. Okay, back to the business of throwing more heat and energy into the system. What happens? You get a more vigorous Hadley cell, more powerful Hadley cell, an expanding Hadley cell. So this is one of the possibilities of climate change, that the sort of the down descending center point of the Hadley cell will move north. If it's Durango, Mexico right now, it could be Tucson in a few years more. It could be Socorro. It could be Santa Fe. That's why, in a nutshell, if you want to know what the future weather is going to be, look south. This business that more heat energy causes the Earth's atmosphere, and I should say its ocean currents, to do more of what they're doing now, is the basic idea behind the saying that climate change is going to make the wet places wetter and the dry places drier. As the system will be energized to do what it does, only more powerfully. And more powerfully means also with more extreme weather. Floods, tornadoes, hurricanes, typhoons, drought, extreme heat waves, all those things. Extreme forest fires. I know, the things that have been happening in Pakistan on the Indus River and the floods that killed the Pakistan rice crop last year, and the fires across Siberia, and the fires in Arizona through this month, and the floods on the Mississippi, and the tornadoes in the Midwest, and the floods in Queensland, Australia, and all these things. These are completely separate events. There's no connection between them, unless you want to begin connecting the dots. These are the kinds of things that the climate change model says we should expect. Now, you can't say that any one of these things was the result of climate change. But if climate change is happening, this is how the scientists are careful about this. If climate change is happening, this is what we expect to happen. People in Washington, D.C. can't seem to connect the dots, but I think you in this room thinking about it might be able to connect the two of them. Let's go to the next slide. I'm talking a little bit. So, this is from an article, Richard Seeger, a fellow I interviewed in New York in the fall of 2009. Very interesting fellow who did some work on climate in the Southwest by accident. He was doing research. He's at the Lamont Doherty Earth Observatory, a unit of Columbia University. Sager's a Brit. He was looking into trying to model monsoon behavior in the Indian Ocean. And he was drawing on an interesting database. In the 1840s, the Royal Navy commanded its ships all around the world, and Britain was wrapping the whole world with its navy in those days, to record sea surface temperature and wind and air temperature every day. And the U.S. Navy soon followed suit, as did the maritime, the merchant navies of the two nations, and pretty soon all the navies of all the rest of the European powers. And this database of sea surface temperatures is an enormous database, very important database. So Sager was trying to model that and figure out how you might be able to predict monsoon behavior in the Indian Ocean, when a colleague of his at NASA GISS, actually, next door, another unit of Columbia, you could say, came up using his model to predict the, and found that it very well predicted the drought of the Dust Bowl of the 1930s. So Sager said, well, I'll try my model and see if it will predict the drought of the 1930s. And it did. Moreover, it predicted, this is based on the sea temperatures, moreover, it predicted the drought of the 1950s here in the Southwest. So all of a sudden, Sager becomes a Southwesternist, and his whole lab does. And this is how this kind of model work is done. You build a model, and you retrodict. You see if the model would have predicted things that actually happened in the measurable past. If it did, then you're on to something. Well, he was on to something. And so if it predicted things in the past, if it retrodicted things in the past, how about running it into the future? Well, he ran it in the future, and this is the conclusion that he reached. There's broad consensus among climate models that this region will dry in the 21st century, and that the transition to a more arid climate should already be underway. Let's go to the next. Sager's subsequent work was in part a reaction to this. This is the, what was it, the fourth assessment of the Intergovernmental Panel on Climate Change, the IPCC. And the IPCC is what won the Nobel Prize, along with Al Gore, I think it was 2008. And it was, this is data plotted or graphed, mapped from the IPCC's report. And you can see this is way out in the future, 2091, 2100, almost a century away. Who cares? Too far to be very significant. But you can see these are significant mean temperature increases. And Sager thought, well, what about near in time? And how do we make this more immediate? Incidentally, the predictions of the IPCC have held up rather well, with the exception of one big matter, and that is that the changes seem to be occurring faster than the models predict. And there's reasons for that, about including as many feedback loops in these giant models as are actually at work in the world. But let's go to the next one. When Sager was looking at things, he was running his predictions not to the end of the century, but to the middle of the century. And what he was finding is that there were going to be big changes by 2050, by 2040, that the changes should already be underway right now. And so he said the levels of aridity of the recent multi-year drought, or the Dust Bowl, and the 1950s droughts will become the new climatology of the American Southwest within a time frame of years to decades. So not at the end of the century, but pretty soon. And what he means by the new climatology is that we'll still have wet periods and dry periods, but they'll be overlain on a base level that is much drier than the recent past has been. The new climatology is that the Dust Bowl kind of conditions and the 1950s kind of conditions will be normal. We don't say that the Sahara Desert is experiencing drought. Right? Drought is exceptional. Drought is not normal. What Sager is saying is that drought-like conditions are going to become normal. What we call drought now will become normal here, or is becoming normal here now. Let's have the next one. Another guy I talked to in the course of doing the book was Chris Milley. And by the way, the book, I try to tell the story about how these guys came to their eureka moments. How these scientists discovered what they discovered that their colleagues thought was important and that they themselves thought was very important. Chris Milley, PCD Milley, works at the Geophysical Fluid Dynamics Laboratory outside Princeton University in New Jersey. Chris Milley is an employee of the USGS, the Geological Survey, but he's attached to a NOAA, National Oceanic and Atmospheric Administration, research site. The idea is that the NOAA guys know the air and the water, and they need somebody who knows about land to work with, and that's Milley's job in his research group. What they did is looked at another database worldwide, which is the flows of the world's rivers. How much water entered the ocean from the Amazon over all the years that it's been measured, and the Orinoco and the Yangtze and the Zimbabwe and every other river for which there was a record. And this becomes a giant database, the Mississippi, and he tracked that against the main climate models in the IPCC system to see if the models would retrodict, if the models running backwards would give an accurate figure for the actual measured outflow of the Mekong and the Yangtze and the Rhine and all these other rivers in the database. Turns out, yes, they did. And Milley, when he said this, he made a motion like this. He was astounded. He was a climate change cynic before he and his group found that these models very, very accurately retrodicted the flow of rivers. Okay, so if they did that, Why not run them forward and see what they're going to do in the future? Well, this is the graph of what stream flow would likely be over the next, what period? Over to mid-century, basically. And you can see the areas of declining yield and rising yield is the blue. Wet places getting wetter, dry places, in general, getting drier. Southwest getting much drier. Only the places that had at least 2/3 of the models agreeing, and not just the models, but the model runs, because a model run, depending on what its starting point is, will be different. So the 60% of model runs had to agree to have any color at all. If it's white, it means that there was ambiguity about what the models were saying. If there's cross-hatching, it means that over 90% of the models agree on the direction of change. So this is our peak at the future for the Southwest. A lot less water. In fact, it was at a Quivira Coalition annual meeting in 2005, shortly after this paper was published in Science. Was it Science or no, in Nature? I was sitting in the audience listening to Jonathan Overpeck, first-rate climatologist from University of Arizona, give a presentation. And he put this slide up, and it really woke me up in my seat. I looked at that, and I thought, we're in deep trouble. And that moment was really the origin of the book. Because I realized, we're not talking about this the way we ought to be talking about this. Incidentally, one other thing, if you look over here at the most water-stressed region of the globe, in the future, the area where the decline will be greatest, you might notice a certain convergence with places under stress today, politically, militarily, etc. There was another time when Milley, as we were talking, made this gesture. And that's when he said, after he got this map, he pulled up a map of the places in the world that are already living beyond their water budgets. And he compared it with this. I'm not drunk, officer. Let's have the next slide. Almost all model runs agree on the direction of 21st century change in certain regions. Prominent regions of agreement on decreasing, typically 10 to 30% of runoff, include Southern Europe, the Middle East, mid-latitude Western North America, that's us, and Southern Africa. Next one. So here's a kind of zoom-in map that's just, the units are a little different because they're watershed units, but you can see that the lower Colorado area here is sort of in the center of the water decline bullseye. And the Rio Grande is not far behind. Let's go to the next one. I want to keep an eye on the time, too. This is just a shot from Hoover Dam at Lake Mead. I think it was December of 2010. And you can see, Lake Mead, because of the snowy winter in the northern part of the West, in the northern part of the Colorado River watershed, the lake's going to come up this summer. It is coming up now. But at this point, it was just a little bit away from its lowest point, its breaking of its lowest point in the 1950s drought. What you see here, this white, this calcite, is the famous bathtub ring as the lake goes down. Let's look at the next one. So this is an actual graph of Lake Mead. It doesn't have the uptick that we'll have this year. The lake may rise as much as 23 feet this summer, some modelers say. But this is an interesting kind of history of the West in these water levels. Here you see the 1950s drought, which actually, okay, the 1950s drought, which was the lowest point until just lately. If we can get back to this one. There we go. So we've beaten the 1950s drought. This other low point, I know you know. Anybody know why the level went down at this time?
Lake Powell.
Exactly, exactly. 1963, they closed Glen Canyon Dam and began filling Lake Powell. And so it wasn't a question of drought so much as just allocating that water to Lake Powell, trying to get both reservoirs full. And as Lake Powell filled, well, more water came through to Lake Mead. So this level right here is the level at which two things happen. One is the shortage declarations come into play on the lower Colorado, and also at this level Las Vegas will lose its number one intake. Las Vegas draws all its water out of Lake Mead, and it's the director of its water operations, Patricia Mulroy, a rather conspicuous figure in the West, whom I had the privilege to interview at Bishop's Lodge 2 years ago. And boy, is she a piece of work. She's really an impressive woman, maybe the most powerful woman in the West. And that day, she was wearing a beautiful cream-colored suit and gold lame ballet flats. And, but she's the kind of person, when she looks you in the eye and expects a nod of agreement, you nod in agreement, because her voice is kind of like a headlock on you. If you say no ma'am, you regret it. But at any rate, the lower Colorado, the lower basin of the Colorado, the states of Nevada, California, and Arizona, and New Mexico has a slight interest there, but it's not big enough to worry about, unless you're a state engineer. These states, and principally California and Arizona, are in a deficit mode. They consume 1.2 to 1.3 million acre feet per year more than their allotment under the Colorado River Compact. Their allotment is 7.5 million acre feet. So you can see their overage, 1.2 to 1.3, is a fairly large percentage of 7.5. And I won't try to go into all those numbers to make you dizzy, to go through all the sort of accounting of the lower Colorado, although it's in the book. But the fact is that even without climate change, the lower basin states are overdrafting their account by that amount. Who says it's that amount? Well, there's been a lot of discussion in scientific papers and in managerial circles about how much that overage is. That's a number I got over the telephone from Tom McCann, who's the operational manager of the Central Arizona Project. He's not a pointy-headed academic. He's an actual water manager. It's also the number that researchers from the Scripps Institute came up with as they examined the future prospects for Lake Mead. And they came out with a paper that said after 2030 or so, factoring in climate change and analyzing the full water budget of the Colorado River, there was a skyrocketing chance, a better than 50% chance of Lake Mead's failure. That is the lake's level going down so low that you can't get water out over the dam, through the dam. Lake Mead's failure. Well, that paper caused a hell of a stir, and people at the Western Water Assessment, which is headed by Brad Udall, nephew of our beloved Stuart Udall here, Brad and his people began examining the work of the Scripps people, and they found errors in it. And They found errors. Actually, I gave you the wrong number before. Originally, they had said the failure was going to skyrocket after about 2020. The errors identified by Western Water pushed it out to 2025. I know that should make you feel a lot better. Downstream of Lake Mead, there are about 30 million people who depend in full or in part on the Colorado River for their water. Now, if the Colorado is already overburdened in a deficit situation, consuming more than there is water, and the way they get by with that is because the lake has a big storage capacity being drawn down, and because the upper basin states haven't used their allocation. So the lower basin has become addicted to the underutilization by the upper basin of its share. But the upper basin is using more and more, and that's part of what this budget examination showed. So that the chance of lake failure goes up and up, and if the predictions of climate change are correct, that total yield in the system is going to decline by 10 to 30%, then failure becomes almost certain. Next slide. The folks most vulnerable are the CAP, and this is a map of it. CAP stands for Central Arizona Project, and this is the big water moving project that came online about 10 years ago and delivers water from the Colorado River all the way to south of Tucson. In order to get this project approved by Congress, the Arizona congressional delegation had to cut a hell of a deal with California. California had a much bigger congressional delegation, still does, of course, and they wouldn't let authorization of the CAP go through unless and until Arizona agreed that the authorizing legislation would expressly make Arizona's rights in the Colorado River subordinate to California's rights, which is to say that if there's a shortage, then California doesn't have to absorb a pro rata share of the shortage. All the shortage is absorbed by, or almost all, because it doesn't apply to all of Arizona's rights, but all of its CAP rights. Arizona has to absorb California's shortage share as well as its own. So this is a very odd kind of situation that pits Phoenix against Los Angeles, Tucson against San Diego. Let's go to the next. This is a picture of the CAP running through Florence, Arizona. Next slide. This is a reconstruction of the mean flow of the Colorado River at Lee's Ferry, Arizona, going from yesterday back to 765. This is based on the instrumental record only for a very short period in here, and on tree rings for all the rest of the span. There have been several of these reconstructions, and this one is probably the most generous one, and it may also be the best. If we can get the left column here, this study by Dave Miko and Connie Woodhouse and a bunch of cooperators comes up with an average value of 14.7 million acre feet per year over this very, very long stretch of time. The Colorado River Compact, if we can get this corner, the Colorado Compact was drawn up in 1922 based on basically data taken from this period, which is one of the wettest in the record. The allocations within the compact are premised on the idea that there was reliable water in the Colorado River of about somewhere, we don't know exactly what the people who signed the document were agreeing on. Some probably were working from different base bits of data. But basically, they were in the range of 16.7 to 17 million acre feet per year. And what we have in the record is 14.7. So you can see there's a problem right there. The obligations under the compact are 7.5 million acre feet to the upper basin and 7.5 to the lower basin. That's 15 million acre feet. And then in the 1944 or 45 water treaty with Mexico, we assured Mexico 1.5 million acre feet. So it's at 16.5 now. Plus, the system evaporates about 1 million acre feet in those big reservoirs, Powell and Meade and some others. And so that's 17.5. So we're already above the assumption of the time of the writing, and we're very far out of line from the long-term reconstructed amount. Also ignored in all this is the concept of mega drought. You see one here. This is the one that brought Chaco Canyon low. Here's the one that helped bring Mesa Verde and the rest of its region low. We haven't, in the historic period, had droughts like these. The drought of the 1950s was here. That's the worst in recent human memory. And you can see it doesn't really compare to the mega droughts of the past.
What about the late 1800s? It's like, what is significant?
That was a pretty significant one. It sure was, yeah. Let's go to the next one. So this is basically what I said earlier. This is again from Seeger. The most severe future droughts will still occur during persistent La Nina events, but they will be worse than any since the medieval period because the La Nina conditions will be perturbing a base state that is drier than any state experienced recently. Let's go to the next one. This is just a joke slide. This is the Gila River passing through Florence, Arizona. And the way in Arizona, the way you tell that there's a river is by the aggregate plant. If you see a pile of gravel and sand, that means there's a river. Water is not a good indicator. Next slide. So what happens? Well, this is a slide by somebody some of you know, Craig Allen. That's the Cerro Grande fire blowing up. year 2000, after a punishing drought. Next slide. This is a table that takes a little time to read, but it's a and this is a composite of fire scar research undertaken by the Laboratory of Tree Ring Research at the University of Arizona and its colleagues throughout the West. And each of these lines is a different place, a different site, 25 to 250 acres. And at least a couple of dozen trees within each site. These tick marks are fire years. The trees have fire scars on them. Sometimes a tree that's burned once then will record many subsequent fires in that healing bit of bark growing back over the burned area. And so you can get a dozen fires recorded on a single tree. So these are all these sites and all these fires, and what you see here is that in some years, virtually everything burned. Well, those years happen to line up with La Ninas, like we just had. This is a year that would be a fire year. But something really interesting happened right around 1900 in the 1890s. These natural fire rhythms just stopped. Dead as a hammer. Why? Well, mainly grazing. The removal of fine fuels, the grass fuels that carried light fires through ponderosa and mixed conifer stands, followed by entire fire suppression. There are some exceptions here, but the exceptions prove the rule. This A is from the Chusca Mountains, where the Navajos began running substantial numbers of sheep in the early 1800s. This section, B, is from El Malpais National Monument, where air attack was the only way to deal with wildfire, because the land is so rough you couldn't get crews in there, couldn't get vehicles in there. And so the fire regime continued on pretty much until air resources became generally available after World War II. And this, where the fire regime continues more or less intact till recent times, is a very isolated location in the Sierra Madre of Mexico. Next slide. So, what happened because of the cessation of natural fire, you all know very well. Now we have terrific fuel buildup in the forests throughout the Southwest. The Wallow fire, which is still burning in eastern Arizona, wouldn't have burned so bad but for the extraordinary amount of fuel there because of the cessation of the natural fire cycle. When you combine that with increased temperatures, you get the kinds of gigantic fires that the Wallow is, and that its great predecessor, the Rodeo Chevascai fire on the Mogollon Rim in central Arizona, was in 2002. The Rodeo Chevascai burned 467,000 acres. Remains to be seen if the Wallow is going to exceed that or not. But basically, you've got two things going on: increasing heat, increasing temperatures, and extraordinary fuel loads. And if you want to know, is climate change involved here? Yes, it is. Tom Swetnam of the U of A Tree Ring Lab and Tony Westerling of University of California, Chico, published a very important article in Science that correlated increased size and vigor and frequency of fires in the western U.S. with climate change. Next, please. Oh, if we can go back real quickly. Here's part of what's going to be really interesting. These big fires blowing gigantic holes in what formerly, the Mogollon Rim used to be the largest continuous ponderosa pine forest on the planet. But these holes are too big for ponderosa to recolonize. What you see out here, this is juniper coming in. These landscapes, in the aftermath of these fires, are moving towards something we don't know what it will be. They're not going to be coming back as ponderosa pine forests. Not for centuries and centuries and centuries, maybe never. So we're going into territory, ecological territory, that is unmapped, a future that is unknown. Let's have the next one. We usually think of the changes in our world as being big, powerful, dramatic things: fire, flood, tornado. We don't think of insects as being radical agents of change. But this is a picture from the 2002 Pinon Ips beetle breakout from here in northern New Mexico. And you all know the story about that. I'm running out of time, so I'm going to go quickly. Let's look at the next one. Yes, I was hoping it was that. This is a map of beetle impacts on forests in western North America. Here's the Pinon Ips beetle and the Ponderosa Ips beetle down here in the blue. There's a little bit of spruce beetle activity down here in a few places, a good deal up here in British Columbia, and there's a lot of mountain pine beetle activity up here. The time scales are a little different. The Pinon beetle was just during our drought episode. The mountain pine beetle, well, what's mapped here goes back to 1980. But you can see a lot of impact one interesting thing, the mountain pine beetle used to be held on this side of the continental divide, but a warming climate and strong winds have now pushed the mountain pine beetle over to the eastern side of the divide, and if those beetles adapt to jack pine, which is continuous, then Katie, bar the door. You all know the story about beetles. I'll summarize it very, very quickly. But as temperatures rise, you have warm winters. You don't have a kill of the beetles with really strong winter loads. Moreover, spring comes earlier. They become active. The growing season, the summer season, the breeding season lasts longer in the fall. They can have more reproductive cycles in a year than otherwise. So that as they reproduce exponentially, you can get loads of beetles so great that when they attack even a healthy tree, they can overwhelm it. But when things are really hot, things tend also to be very dry, and the trees are dehydrated. And because they're dehydrated, they can't muster their primary defense against the beetles, which is when they drill into the bark of the tree, a healthy tree would flush them out with a flow of sap. A dehydrated tree can't do that. That's why you have these sort of cascading effects, big die-offs from these beetle effects. Let's go to the next. So, this is also from our area, and you all are familiar with the impacts of beetles here. Let's go to the next. The book tells the story of, if you want to see climate change at work and impinging on wildlife, look at the top of Mount Graham in Arizona. You all probably remember the big fight over the Mount Graham red squirrel in the late 80s, early 90s. The question was whether an observatory, the Mount Graham International Observatory and the Pope Scope over here and the German observatory here, should be built in the restricted habitat of the Mount Graham red squirrel, an endemic species dependent upon the top of the mountain. Well, to make a long story short, the squirrel has really seen tough times. If climate change were to happen, we would expect the top of a mountain like Mount Graham, which has a kind of relic stand of spruce and fir, we would expect that stand to be attacked by beetles and by fire. And both of those things have come to pass. And in this slide, you can't really see it, but nearly all these trees are dead, and some of them have been burned or are just standing carcasses. So Mount Graham is a place where both fire and insects have worked their destructive magic aggressively. Let's go to the next one. Oh, and there's the protagonist. Very cute, much smaller than the International Observatory. Let's go to the next. Another impact of climate change in our region, I believe, is that some of you may know Rebecca Solnit. She wrote a very fine book about how people in catastrophes tend to pull together. Survivors of the San Francisco earthquake in 1906 talk about an almost utopian spirit in the aftermath of the earthquake and the fires that followed, because everybody was of the same condition suddenly. Rich and poor, everybody trying to just pull together, and people really helped each other. Sudden dramatic calamities do that to people. A drought is different. You don't know you're in drought until you've been in it for a while. You don't know when it's going to end. It's not sudden. It goes slowly, creepingly, like a kind of cancer. And it gives you plenty of time to reflect on all the fallibilities, all the negative points of character of all your neighbors. And your neighbors get to reflect on all the negative points in your character over a long time. So my hypothesis is that climate change is going to add stress to all the existing fault lines within the society of our region. And to borrow a phrase from Saddam Hussein, the mother of all fault lines in the Southwest is right here, the international border. And if we think things are bad now, as climate change continues its work, they're going to get a lot worse on the border. There are some academic papers that forecast with X amount of increase in temperature, we'll have X million more people trying to come north over the next Y number of years. All those kinds of projections are very, very speculative, but the fact is that there's a lot of stress in our society already. Next slide. This is just some art from the border in Nogales. If you get to Nogales, walk through at the old crossing down in the bottom of the canyon, hang a right, and this is on the Mexican side. There's about a kilometer or a kilometer and a half of really spectacular wall art on the border wall all along. These are walking feet, and if you go to the next slide, you'll see how those images are made. They're made of thousands and thousands of photographs of individuals. Next slide. This is the shrine of Jocelyn Hanifa, I can never remember, Hernandez Quinteros, a 14-year-old girl from El Salvador, whose body was found by aid workers in the desert near Aravaca. More people have died crossing the border in the desert than the U.S. has suffered casualties in both Iraq and Afghanistan. This is not a war, but it has warlike casualties. Let's go to the next. Let me wrap this up. Again, Chris Milley, and I'm not doing justice to this material. I ask your forgiveness for skimming over a lot of things here. Stationarity is an engineering concept. When people talk about a 100-year flood or a 500-year flood, that's based on ideas of stationarity, that if you're going to size a culvert or a retaining structure, you do it based on your prediction, your assessment of what a 100-year event is going to be. When Chris Milley and Julio Betancourt and the others wrote this article, they were saying those kinds of models about how the Earth works have to be thrown out. Because with climate change, these kinds of standards, this kind of predictive circularity in events, goes out the window. It's just like what a stock prospectus tells you. Past performance is no guarantee of. Okay. So it's caveat emptor all the way. Next slide. So we're going to need to have new models for prediction. And those models are being developed. But it's a new world. We're going into uncharted territory. And that, I would submit to you, is what irritated people the most about this fellow, Mr. Darwin. It wasn't just that he posited a world in which a benign God was not pulling all the strings all the time. He described a world in which creation was unfinished and went on and on and on, ramifying into the future with no particular destination. There was no address to which we were headed. We can talk about Herbert Spencer, who tried to provide that address, and other things. Darwin didn't give an address. Creation goes on, and if you read that last sentence, which I wish I could recall from memory, of Origin of the Species, one of the most beautiful sentences in English literature. Evolution goes on and on, creating beautiful, most wonderful creatures ad infinitum. We're headed into new territory, my friends. That's what climate change is bringing us to. And if you really like to see the world change, you've been born into the best time you possibly could be born into. But if you get attached to particular places, to a particular stand of tree, behavior of a particular river, you could be very disappointed because a lot of things are going to change. I think that's the end. Is there anything? Oh, last idea. I took this picture in the company of that gentleman, Phil Smith. You see a rapids. I think this is Tapeats Rapids, actually, but I'm not sure. Anyhow, the metaphor in my mind for climate change is like these rapids. If you're going down a river and entering a rapid, you can control three things: your point of entry, your velocity at entry, and your angle at entry. That's it. If you don't get that right and you're going into a really tricky rapid, then you're toast, right? You still can't control everything on downstream from there, but if you get that first point of entry right, you've got a good chance to be able to continue to react and respond as you go through. If you don't get that right, you just surrendering yourself to chaos from the outset. I think of climate change as rapids. I think of our position as still being up at the top of the rapids somewhere where we have a chance to get hold of our point of entry, our angle, and our velocity. Are we going to do it? Thank you very much. I know I've gone too long, and some of you have to clear out and go back to work and do things like that. But if anybody wants to stay and talk, I'm happy to do that. But feel free, if you need to leave, make a run for it. Yes, sir.
I want to ask about adaptation. There's often debate about prevention versus adaptation when it comes to climate change. Richard Sellers, retired National Park Service guy, talked about the enormous growth of pinyon juniper within the city limits in the Sunday opinion piece in New Mexico. And not having lived here at the time of the Los Alamos fire, thinking about, but having lived in California for a long time, where now there are a lot of requirements about how and where you can live and clearing requirements and that sort of thing. That it strikes me that Santa Fe is sort of kind of a dream world in the sense that we do live in a place that is tremendously vulnerable. And little money, time, foresight is spent on trying to figure out how to cope with it.
Right. There are basically two broad areas of response to climate change. One is mitigation, which is lowering greenhouse gas emissions and trying to get back. I omitted to say that James Hansen and others agree that we need to get back to 350 parts per million. We're at 390 now. It says if the departure from 350 is not brief, we may see irreversible changes to the Earth's climate system. The other area, as you say, is adaptation. So what should we be doing to adapt to the changes that are already in the system? And this system has enormous inertia. I mean, we could stop greenhouse gas emissions today, dead flat, and the climate will continue warming for decades. We've already created the climate of our children. We're working on creating the climate of our grandchildren. So what should we do? Well, the interesting thing to me is that what we should do is basically the same stuff that we should have been doing anyway. We should be moving our forest systems to a more stable and fire-resilient character through thinning and other kinds of treatments and prescribed fire, especially in high-priority areas. We should be moving toward a sustainable water budget in our southwestern communities. We should be working on those fault lines running through society, all those things. Santa Fe, as Frank says, is vulnerable. The area out, Old Santa Fe Trail, scares me when I look at that closed canopy, pinon, really forest, not woodland anymore. Fire gets into that, there are an awful lot of homes out there. There's no way you're going to stop that fire if it has a wind behind it. There are a lot of communities, a lot of suburbs, a lot of neighborhoods, I should say, around Santa Fe that are very, very fire vulnerable. But even more than that, our whole community is water vulnerable. And so is every community in the Southwest. And we haven't, here's the big thing, if you'll pardon a quick digression. Water conservation is essentially a hoax. It doesn't make our communities more stable, more resilient in terms of water. For this reason. If I xeriscape my yard, and you get a low-flow toilet, and you take short showers, and all of us do all the things that we should do, what happens to the water that we save? Growth. It goes to the next subdivision, it goes to the next strip mall, down the line. And what happens as that process moves forward? It's a phenomenon called demand hardening. In the bad old days, when we wasted a lot of water, maybe 50% of our water use was essential, and 50% was something we could do without if we had to tighten our belt. So when drought came, you get rid of discretionary 50%, watering the lawn, things like that, washing the car, and you make it through. But if you're conserving, and you're conserving, and you're conserving, everybody in this room is conserving, 90% of the water we use is essential. So there's not much flex in the system. Demand has hardened. So what do when supply drops? What do when climate change results in a substantial decrease in the flow of the Colorado, the Rio Grande, etc., in the recharge of our aquifers and all the rest? We're painting ourselves into a tighter and tighter corner. And it would make sense that we could deal with this by limiting growth. But where has that been done? Well, one place it was done was Bolinas, California. Bolinas, California decreed that only a certain number of water meters would be allowed. Past that, no more. In 2009, in April of 2009, a water meter exchanged hands in Bolinas, California for the tiny sum of $300,000. You restrict demand, you restrict supply, demand goes up, price goes up. In most communities, that would be viewed as a violation of human rights. All people should have access to water. How do you deal with this? How do you square this circle? Nobody's figured it out yet. And until we figure it out, we cannot have a really defensible, sustainable water future in any of our arid land communities. Yes, sir.
Do insurance companies or public agencies create maps of fire vulnerabilities?
I think some insurance companies are beginning to do that, but I do not believe it's a widespread practice at this stage. And that's really, on the matter of fire defense, where the change is probably going to happen. I think the insurance companies are pretty much asleep on this one.
They have done
Excuse me?
it. They have done it.
They have done that?
In California, yes.
I can't hear you.
In California.
Yes, sir.
I was happy to read this morning in the paper that our drought here is going to end in summer with heavier monsoons and much heavier cloud bursts. I only read the caption under the picture, so I have to go and read the rest. Have you heard anything like that? Are we headed for a huge rainfall?
Well, some people say that there is a correlation with drought ending with a lot of winter drought ending with more vigorous than average monsoons. And there's some data that supports that. Studying monsoons is really difficult, and there's not very much consensus on that yet. But that's a strong theme. And incidentally, the idea that with climate change, with more energy in the climate system, we can expect more really big storms, including summer thunderstorms, more flooding, more arroyo cutting. And arroyos and the sort of geologic and human accelerated cycle of down cutting and building up and so forth is part of this story. And it's likely that we're entering into a period where we're going to see a lot more arroyo cutting, more vigorous storms, just as you mentioned. Yes, ma'am.
You were saying that the one way to make a difference is to limit growth. Is there any other way that population can make a difference in limiting the situation that's going on?
I honestly don't know. I don't know the answer to that question. I think about it all the time. I think we need to start experimenting on these matters. I think that creating some kind of serious and defensible conservation water reserve is essential. I think just because we free up some water through conservation activity doesn't mean that we should reallocate it for community growth. Somehow we have to find a way to hold it back and keep it as a reserve. But I don't have the answer there. I think we have to work toward that answer as a community. Yes, sir.
There's social issues too, unfortunately, because when you say don't build a super Walmart, then you're accused of being racist.
That's right. Oh, everything ties into this. Everything ties into this.
Limit population growth would be another one, and that's controversial, but that would help.
Yeah, Phil?
What the article in the paper this morning didn't take into account is that they were looking back at history for monsoon model, and the situation has changed. That history is no longer perhaps appropriate.
Well, that's, stationarity is dead. The past is not necessarily a guide to the future.
Thank you.
Thank you very much.
All right.
Thank you, Phil.